are saying like you get this much combined singleton noise. And ultimately, the number that you get is about 380,000 Type Ia supernovae with good-ish quality light curves, and roughly 1 million with all over the place quality light curves. For DDF, the numbers are much smaller. You just don't have that much area. It's somewhere between 10 to 15K. But the key thing here is to compare it to where we are now. So everything I've kind of talked about so far is the red, and this is on a log plot. And really, we're going from 2-ish thousand to potentially 400,000, which is just an amazing jump. Now, kind of the hard part about this, kind of what I've mentioned before, is that to do the science we want to do, you need to get redshifts, and basically what we're saying is we want to get 400,000 redshifts across 18,000 square degrees, and there's a lot of discussion now about what's the instrument that will do this. So is it a lot of foremost, a little bit of DESI, and some mixed match of a bunch of other things, or what's going to be able to do it so that you can get 400,000 galaxy redshifts across just a huge amount of the sky? Yeah?
In theory, LSD was like photoses.
Right.
How useful that actually is.
Yeah, so this is one of the big things I'm working on is how useful photoses are. So the hard part is basically, so you have the host galaxy photosy prior, and then what you could also do is you could fit for the supernova redshift with the other parameters you have in your light curve fit. So you could basically use that host prior plus add it in as a fit, and the redshift is covariant with the supernova color, and a lot of our worst systematics are with the supernova color. So right now it seems promising, but we haven't kind of convinced ourselves that this will work. I'm just not sure, so I'm a student working on it, but it feels like, I don't know, maybe if photoses got better, this could work, but we're not there yet. But that would kind of solve our biggest problem. Okay, so what I've said so far about LSST is that there's this kind of nominal survey, and it covers a huge amount of sky, but and it could potentially be the greatest thing ever, but it could used to be optimized significantly. So the LSST project is very much aware of this, and they set this schedule for the community to say, here's how we want LSST to go. So there's this call for white papers near the end of June, and there's this workshop, and then at the end of November there's this white paper submission, basically saying redesign LSST for us. And then kind of after this, we're waiting on now these new simulated survey strategies based on all this community input, and then we'll hopefully get a chance to say, okay, here's what's good, here's what's bad, and then LSST is starting 2022. So we kind of really need to figure this out soon of how we can optimize LSST. Now, what was really great about the process, or has been great, and also kind of daunting, is that the project pretty much put everything on the table with LSST. So they said that we want this total area to be covered of about 18,000 square degrees. We need to have at least this number of 30-second visits. We need to get this constraint on parallax, and for some part of the sky, you need to revisit that part of the sky. And this one just kind of happens no matter any strategy. This happens pretty easily too. So roughly they say keep the same area and then optimize everything that you want. So that's they opened up a lot of parameter space, a lot more than anyone expected. So along with Michelle Lochner for LSST Desk, we lead basically the Desk Observing Strategy Task Force to say here for all dark energy science is how we would make LSST. So here's how we would do it. We kind of put all this all of our information on a GitHub page, but basically it's an extremely hard problem because the parameter space is so wide open. And what the project did is release a small handful of observing strategies, and we could say, okay, we like this one, we don't like this one, or we like these attributes and we don't like these attributes. And then others, including your own Chris Stubbs, Stubbs basically said, I know how to do it way better than everyone else, and he was right actually. So he came up with this thing called AltSched, which basically it did a couple things. It it had a lot more filter changes than any other survey strategy, and then it kind of had this pre-planned survey strategy. So everything else is done with what's called a greedy optimizer. It says, okay, at this time, here's the best thing for our survey. Whereas his strategy was like, let's scan along the meridian, and we're going to do it in this pre-planned way, and no matter kind of what happens, we're just going to keep along that plan. And you're just a lot less sensitive to optimization mistakes if you do it that way, and it's much better. So we looked at all these different strategies, and we put together these big reports that are now in the archive, and we basically had to ask all these different desk probes. So there's supernovae, and then there's weak lensing, and there's large scale structure. This is an infographic that's trying to put this all together. And there's strong lens supernovae, and basically internally we didn't agree with each other, but we tried to kind of work it out. And the ultimate goal is say, okay, in W naught WA space, here is the combined figure of merit from all these different probes, and that's what we're trying to optimize over. And you could see here basically how much this matters. So this is 3 different metrics. So this is well-measured Type Ia supernovae, which I talked about so far, the number of strongly lensed supernovae, and number of kilonovae that will be found serendipitously. So basically, without LIGO saying, look over there, just how many kilonovae will be found. And so what Stubbs came up with is this alt-sched. So you can see that actually his thing is roughly a factor of 3 times better than nominal strategies. For Type Ia supernovae, almost a factor of 2 for strongly lensed supernovae, and then maybe 50% or so for kilonovae. So we kind of have an idea of the right way to do this, and we don't have to kind of follow Stubbs exactly, but we kind of keep his best ideas. The hard next point is that we are doing things based on what's the best thing for a desk, for dark energy, but people care about asteroids and all different kinds of science, and duking that out amongst all the collaborations is very difficult, and kind of what we would like is absolutely not what a lot of the other collaborations would like. And what's gotten interesting is kind of how this is going to be decided, and it's very unclear, and a lot of people are very angry. So this is called the Cadence Wars, and that's the name, but basically there's just lots of meetings of people arguing with each other for how to do this.
Are there more than one faction? More than 2 factions, rather?
Oh yeah, there's like 8 factions.
Okay.
Yeah.
All of them have a different plan?
Yeah, everyone has their own plan. And so basically what the project has pushed for is basically metrics to say, so they said, we don't want to hear from you anymore. You tell us, you code up some metrics, and then we're going to make a bunch of strategies ourselves and just run your metrics, and then we'll kind of, with some input from some new committee, decide what's best. But doing these kinds of exercises is very hard, and we have not done a very good job making these metrics and making it transferable, and that's true of kind of all these different collaborations. So in
But the region of the sky is not under dispute.
So the size, but you can move it up or down. You can take out areas where galactic extinction is high. So those are the kind of battles that are being waged.
But how can a committee decide whether asteroids are less important than W?
This is I have no idea.
That makes no sense.
No, this.
What you should do is let many flowers bloom. I mean, that's basically.
But how? I mean, this is the question. How do you do that? So, right. So basically, what Desk is most unhappy about right now is that. So we wrote these white papers, and then you could see in all the following steps. There's no chance anymore for science collaborations to have any more input, and we're saying this is crazy. Like, we don't know what you're going to do, how you're going to decide it. We want some input. And that's just not part of the plan right now. So I think we really love the ambition of what they're setting out to do, but the process right now is very confused. And what's at stake is extremely important. I mean, it's hundreds of thousands of more supernovae or not, or for some science cases, it's whether they can do the science or not. But no one's. I don't get the feeling that people are sure about how this process should work out. Okay. All right. So, kind of where we're going is basically this sums it up. That we have about 1,000 supernovae now. In the next couple years, with DES and adding the Panzer photometric sample and a new low redshift sample, we'll have on the order of 5,000 supernovae. And then kind of in the next few years, that's when the real big jump takes place. That's when we go to 400,000 supernovae. And with WFIRST, which I'll talk about in just a little bit, that's 30,000 supernovae. So it's really kind of, if we could do this planning right, we're really kind of at the cusp of this enormous jump. All right, so another question that I put in the title is why do we even need 500,000 supernovae, or whatever this number is going to be? So I wrote this decadal survey paper. This just came out in the archive, and basically, this looks messy on a slide, but it tries putting into one infographic every different type of supernova cosmology science that we could do with this big statistics. So the normal thing is measuring W with the Hubble constant. And the problem I've talked about is that we're going to find all these supernovae. That's kind of the scale of this box, but the spectroscopic confirmation is roughly the point. So basically, we don't have spectroscopic confirmation or possibly redshifts, and that's the challenge. Now for local H0, that's kind of a different ballgame. I'll talk about in just a second, where we need these special calibrator galaxies for peculiar velocities, so measuring kind of growth of structure. Then actually you do need all these big statistics. Basically, you're looking at peculiar velocities across the low redshift universe, and the bigger LSST is, the better. For strong lensing, time delay cosmography, that's kind of a mid-Z program where we just want to find as many of these unique objects as possible. And then as you get to higher redshift, this will be something LSST will struggle with, but WFIRST can do, is you're measuring the magnification distribution at high redshift. So you're measuring weak lensing through supernova